I'll tell you it's a pleasure to be here, and I have quite a challenge before me. I understand that the audience ranges from high school students to professors, and I therefore want to tell a story that will draw upon your insights, your everyday experiences, and hopefully you'll get to see how mathematics and physics and even some philosophical ideas merge. And so let us begin this story with one of my favorite people, Albert Einstein. I will share a little bit about Einstein's theory, but do so by surgically narrowing in on a particular piece of his work. You may know that Einstein became a household name to a prediction he made about how much the sun will bend gravity's light. So here's the basic cartoon of the situation. You have the sun. Here's light coming from some distant star. And you notice this is a curved path. We all grow up learning that light travels on a straight line. But in Einstein's theory, a straight line can actually be curved. And the idea is that straight lines are lines that follow the most efficient journey. And the way you think of it is that imagine you're driving over these gentle hills, these beautiful hills that I've noticed since landing this morning. You may turn, you go up, you go down. Einstein said when light rays travel through the universe, it's as if they're going across this curved terrain. And this curved terrain is what we call space-time. It's a little bit more abstract than just going over a hill or along a curved road, because the bending occurs not only along the path, but it also occurs in time. And some of that I'm going to try and bring across to you today. But in any event, he predicted that light rays will go along the terrain in space and time and follow this bent path. And he predicted exactly how much it's going to bend. And it was this prediction that separated him from Isaac Newton and gave birth to this whole new set of ideas that in many ways I'd say shifted our understanding of the natural world. And we all talk about things being relative, i.e. space and time. So let's continue the story. When I mentioned about a light ray passing by the sun, here, for example, you have a satellite on the other side of the sun. It comes, it bends. This picture tries to tell you how the spatial geometry bends in the vicinity of the sun. But there's something else I'd like to mention here. Most of the talk will talk about this bending, but in addition to that, there's actually a delay. So that is how it gets affected in time. And this may sound esoteric, but most of you have iPhones and other smartphones in your pockets, purses at this moment. And I bet a lot of you have used the GPS technology that's built into those phones. For GPS to work, you actually need Einstein's theory. And so I'll just tell you 1 minute about how that works, and then we'll continue the story. The idea is that the GPS constellation system is some 24 to 32 satellites going around the Earth, and they give your location by identifying where this is on Earth. And so you have a transmission between this and the satellite overhead. But the satellite is moving. And when the light rays move through the Earth's atmosphere, it's being influenced by the Earth's gravity. So Einstein's first theory, his special theory of relativity, states that time on the satellite will be different from time here. And that the motion of the satellite will cause the clock on the satellite, a very precise clock, these are atomic clocks, will cause it to fall behind. And will fall behind about 7 microseconds per day. Now, it's going through the gravity of the Earth, and that is this terrain that I'm talking about. This is a curving of the space-time around Earth. Sounds fancy, right? Einstein's theory predicts that the gravity acting on the light, in other words, the gravitational lensing, is going to do the opposite. It will cause the time on the clock to speed up by about 45 microseconds. And so the end result is they're fighting each other, but the gravity is more powerful, and it nets at 38 microseconds per day. It's ahead. That simple thing, if you do not take it into account, the whole GPS constellation system becomes useless. And so I'd encourage you to Google GPS and relativity to learn some more about that. So that is one of the ways that gravity acts on light. It acts on it in time. But now let's continue the story with the action in space. A lot of people are not aware that after Einstein developed his theory, I think he was about 57. I couldn't get a good picture of him at age 57, but I think that's a close enough approximation. He wrote an innovative paper. In fact, we should really call it an essay. It was just a page and a half. And I encourage you to look it up. He wrote it in 1936, or I could send you a link to it. In that paper, at age 57, he proposed a very interesting idea. In addition to the bending of light rays, he said the following. Imagine we're here on Earth. Here's a star in the foreground, and then you have a source, another star in the background. This dashed line, we call it the line of sight, so it's a line along which you're looking. If the source of light is off the line of sight, he said, in principle, you're going to see two images of that background light source. Interesting. So you'll see double images being created due to gravity. And in a sense, we could think of it as a big cosmic mirage. In the same essay, in that same page and a half, the other leap he had, the insightful leap he had, is that if you take the source, which is off the line of sight, and you bring it closer, these images are going to get brighter and merge and suddenly create a bright ring. And this is today called an Einstein ring, in honor of him thinking up this idea as early as 1936. So why am I telling you this? Well, first, you're seeing that gravity can really act on light in these interesting ways that you otherwise would not have expected. Well, what we're going to do today is to reinterpret that essay from a somewhat interesting twist. If the source of light, as it gets closer to this line of sight, it suddenly gets super bright, then it must be there's some kind of shadowing going on in space. Because if over here I am very bright to you, and here I am less bright, and I didn't increase or decrease the amount of light I am emitting, then it must mean over here I'm in a sort of darker area. And when I get here, I come into the light. When you do the analysis of this, you can actually do a cartoon representing what's going on. Imagine you have a star here, and then a source of light. I have a big flashlight and I'm going to shine on this star. The light will go out. The gravity of the light, by Einstein's theory, it's going to bend it, and then it's all going to start to pile up on the back. So all these, imagine cannonballs flying, and they're piling up on the screen in the back. In the back here is where you're going to get the shadow pattern being formed. And the essay tells us that when you're if you stand right at the center, you will appear very bright, and not only very bright, you'll look like a ring. When you move away from the center, you'll get less bright. The ring will break into two images, as in the essay. And the further out you go, the dimmer and dimmer one of the images will become. And so this is one of the simplest examples of a shadow pattern being formed behind a star. Now, all of this might sound very theoretical. This may sound, again, Mr. Einstein coming with these esoteric ideas. But we already learned that without his theory, you're not going to get over to this new location across town. So let us see if this prediction has some meat. Here, on the left, this center is right here. And then I don't know if you could see very well from my position, you'll see that there are different rings that mark areas of brightness. And the further out you go, the darker it will be. So this circle that you're seeing is an example of one of them. And then this line number 1, it is, let us say you have a background source of light that you're observing from here, if you wish. It passes across and cuts over the top of one of these rings. And so that's that. Here's another trajectory where it cuts across and on and on. So I'm giving you a sample of 5 trajectories. Well, what the theory predicts is that if you're far away from this point, caustic means burning bright. So this is the brightest part in this shadow pattern. If you pass out from here, your brightness will do that. So here I am cutting across the shadow. You're looking at me. My brightness peaks, and then I dim out, and you won't see me as well. And you do the same thing, and notice the closer you get to the caustic, the taller that peak becomes. Okay? Well, you get a very nice symmetric curve, very nice brightness profile. And that, again, is when the deflector, or the lens, is a star. Well, let's continue the story. You may have heard about planets outside of our solar system. And I claim that this is one of the powerful tools that are used for detecting extrasolar planets. Now, we're not going to have just a star, but we'll have a star and a planet next to it. That will create a shadow pattern that's slightly different from the one for just a star. So let us see what that will give us. Here is the brightness profile of a star moving along the background. And I claim that you will get a spike if that star has a planet next to it. I will show you the shadow pattern in reverse. I don't know if you could see that well, I hope. But here the darkest lines are the brightest. And so the light areas like here are the dark parts. The idea, I'll zoom in on it in a minute. Here's the path of a background star. And here we are looking at its brightness profile. And you notice when it crosses that part of the shadow pattern, you see a spike. So this is all theory, right? We're just using some basic Einstein theory to predict this is what will happen. We don't know, right? Let's zoom in. Mathematically, if you trace out the brightest part in this pattern, in other words, you trace out the caustics, it will be a curved shape like this. And you see these points on the edge. And so when the source is crossing, as it hits this first point, you notice the first spike. And when it hits the other side, that is the second spike. Then it goes away from the caustic and it dips back down. Well, you can show that if the radius of that background source that is being lensed by a foreground star and its planet is small, this spike will be taller and taller. If the radius gets bigger, the spike shrinks down. I am going to show you actual data that was collected, I think, from about 4 telescopes around the world. in showing evidence of an extrasolar planet. Here is the brightness profile of a star. Notice how it follows that smooth curve, and boom, there's a spike. That is the signal. And these dots represent the different, I don't know if you could see some of the colors, but these are the different telescopes that are observing the same event from different parts around the world. And each dot is a measurement. The smooth curve is a theoretical fit. It is simply amazing. And so you see that the evidence of the shadow pattern shows up in this brightness profile. And here they inferred that the planet that's next to the star is about 5 times the mass of the Earth. And so they refer to it as an Earth-like star. And it exists, Earth-like planet. And it was a star that was towards the bulge of our galaxy, the center of our galaxy. So you're seeing it's quite amazing that these things can actually be observed. Now here is what the shadow pattern would look like if you have a star, and here by shear, I mean you have a star, then there's some matter far away whose gravity is pulling across it. That's what I mean by shear. Those of you in calculus may have noticed this curve. This is an asteroid curve. Right? You probably learn how to find areas and so on connected with a curve like that. It's a beautiful curve, and what I want to bring your attention to is the yellow part is the brightest, red is less bright, green is less bright. Notice at each point, each cusp point, there's a lobe of brightness. This is less bright, but it's like a flashlight, right? Coming out of these 2 big lobes. Now, you have seen this in everyday life. Sometimes if you have coffee and it's hot, you put cream in it, you should look out for this curve. This is a cusp curve. And notice that on one side it's more bright than on the other side. And here's the lobe. This is it for the star, right, with shear. Notice one side is brighter, where you're seeing the yellow. And so these effects actually show up in everyday life as well. Now, as mathematicians, you want to not just study the shadow pattern due to one star. Well, what happens if you have 2, 3, or many stars? Here's a shadow pattern. I think this is like 50 stars. And again, when you look at it, you see the cusps and you see the lobes of brightness here. Inside is brighter than outside where the green is. It's quite beautiful, right? Now look at this side of a boat. Next time you head to the islands, I'm from Belize, so I see this all the time. These things are actually, they have a universality. There's a generic nature to them that you see these things will exist not only in a cosmic setting, but also in everyday life on Earth. There's something about the laws governing how light is refracted. Let's keep marching on. This is a shadow pattern. And again, these areas, as they look, are dark. Here are the brighter parts. And it's quite intricate. It's a section of the shadow pattern due to about 100,000 stars. And when you look at this, I think it may remind you a bit of neural networks in the brain. What happens, now stars typically are expected to have some kind of planets around them. So what happens if we pick up the contribution of the planets? This is on the scale of the star. The planets are about 1,000,000 times less massive than the star. So you'd think the gravity of the star would dominate the gravity of the planet. But that's not quite true, because we saw earlier, when the brightness curve, that little planet gave you that spike. And so how would the shadow pattern change if you now turn on the planets, which are much smaller in mass? The mass affects the gravity. So here's a picture. Look at that. It's quite amazing, right? Look at the detail and the complexity that emerges when you allow an even finer scale. Now that looks like something out of the brain, right? Well, let's continue the story. As mathematicians, these are not just cute pictures for us, but you ask yourself questions like, are there mathematical laws governing these things? And it turns out that there are. This isn't arbitrary. And it's not just a complex mess. I'm going to show you a series of pictures that's going to zoom in. So here is your intricate web. It's here in black and white. So imagine this big panel. Here's a caustic network, again for about 100,000 stars. And now in this section, that's what you're looking at here. We're zooming in. Here is this panel. And then here is that panel. You notice how you come right back at the lowest scale to these cusps to the side of that boat. Let me do it in color. That's much easier to see. Right? Even in that intricate mess, you go down in scale and you're still back to this basic structure. Well, it turns out that the bending of these curves and the turning on these cusp points follow a particular mathematical law. And I'm not going to tell you what that is. You could leave that for the Q&A. But I'm going to show you a mathematical theorem through a picture. So we may ask the question, are all these shadow patterns with these pointy edges and these lobes of high magnification? And the answer is no, they can evolve. Let me show you. So here is one, look at this left panel. You see the cusps again, right? Here dark areas, these are bright areas. Now what I'm going to do, we have all these stars and you have matter between them. I'm going to increase the density of that matter. And notice what's happening. It's starting to turn inside out. Notice these areas are brighter than that, but then look here, the cusps here. The cusps are almost like they're pointing inside these darker regions. And if you keep hiking it up, notice now they're separating out into blobs of darker areas. Here is one cusp, here's another. This one has none. And if you keep increasing the density, you will eliminate all the cusps. And you can actually prove that as a theorem. And what you end up with actually are geometric objects called ovals. So you find that in certain scenarios you could have no cusps at all. And if you're a little bit into science fiction, well, I'll tell you, if you're looking at a star and it has high density, this will be the shadow pattern that will be created behind it. And it will be a blind spot. And when I say a blind spot, it's like you're literally going to hide into the shadows. And it's not that you just can't see me visually in the visible wavelength. You won't be able to detect me at any wavelength. So there are regions of darkness that no matter what, from your vantage point, you cannot detect what is in there. And so imagine you have a war situation within our galaxy. That's a nice place to hide, right? So I think that from the point of view of these shadow patterns, that is all I want to say for now. And then continue the story on, because I have about until 1:45, right? Great. I want to continue the story into this business of higher dimensions. What on earth does that have to do with these shadow patterns? Well, let us go back to high school days and consider shadows now with geometric objects. So I'm going to begin with a cube, but the cube is made out of wire. And so here it is in space. Imagine you take a flashlight and you shine it down on that cube at an angle. You will actually see a shadow like this. If you do it just right, you could play around with it. See a shadow like that on the ground. Now, you look at this cube and you look at its shadow. This shadow actually contains a lot of information about this cube, you know. You could count the number of faces on this cube, but I claim the number of faces on that cube is captured in its shadow. So let's count. 1, 2, 3, 4, 5. Uh-oh, I'm missing one. Well, that's the outer one. 6. You can count the vertices, and you'll see it all is captured from there. It turns out that this type of shadow, it has a name. It's called a Schlegel diagram of the cube. Geometers study this kind of thing. And now, if we go to high school and you ask what is the shadow of a 4-dimensional wire cube, well, it's not going to appear in the ground. It'll appear in physical space like that. Right? And then we could try and count how many regular cubes form the face of this 4-dimensional cube. And you can, if you could see it well, we could try and count, right? 1 is on this side, 2 on the other, 3, 4, 1 on top, 5, 6, then 7 in the middle, and then the outer one, 8. So what it's telling us, I can't directly visualize this 4-dimensional cube, but I can look at its Schlegel diagram and figure out that this thing is covered up by 8 cubes. So this is some very fancy object, right? Well, let's continue the story. This had such an impression on architects that you may remember, I think it was Meteoron, but if you've been to Paris lately, that was what inspired it. It won the award. The Grand Arch in Paris was inspired by the shadow or Schlegel diagram of a 4-dimensional cube. So getting around and getting a feel for higher dimensional objects, you can also take a shadow approach to it. And let's do one more. Imagine you have a box, so we're looking at a regular cartoon box, and I get a scissor and I start cutting an edge to open it up. So we'll call that an unfolding of the cube. So here's the box, and I cut the top along the edge here. Here I'm opening it up. And then when I open it up, when I unfold it, then I can count the faces, 1, 2, 3, 4, 5, 6 again. So you may ask the question, if I get a 4-dimensional cube and I cut it out, what is that going to look like? Well, some of the high school students here, I'm sure, may have seen this, but it's going to look like this. And we can count the cubes. So if you use the analogy of this one, notice the 6 faces of this box are contained in its unfolding. And so for the 4-dimensional cube, this better have 8 boxes that's supposed to form the faces of this 4-dimensional thing. And if you count 1, 2, 3, 4, 1 in between, 5, 6, 7, 8. Right? Well, I will tell you this. At age 13, back in Belize, I remember seeing I'm a big Dali fan. In fact, I wanted to be an artist. I didn't want to deal with this math science stuff. And I remember seeing this painting, the crucifixion. And at that age, I just remember this is something that gripped me. You know, Dali is a genius and enigma. And for him to have put the crucifixion on this thing. Right? At that time, no one in my little town knew what that is. And then later I grow up and then people say, oh, this thing is a four-dimensional cube. But now as you get older, you realize it's not the four-dimensional cube. It is the unfolding of a four-dimensional cube. Dali interacted a lot with mathematicians. And when he encountered this, he had the leap and said, I'm going to draw a crucifixion scene on that. And he did this brilliant masterpiece with it. And I think, if I remember, he even interacted with Tam Banchoff of Brown University. So if you look at Dali's Last Supper you'll see a higher dimensional object in the background. So it's a beautiful place for art and mathematics to come together. And in fact, my colleague, Ingrid DeBosch, she is doing this semester a whole thing with art and mathematics. So let's continue the story. Well, okay. How do we bring this now to extra dimensions for our universe, right? It's nice to deal with art and some geometry in higher dimensions. Well, I want to tell you a little bit about something from physics called brain world theory. And now there are different versions of this, but I like simplicity. And the one by Randall Sundrum, to me, has the simplest and has a natural formulation. Here's the buzz. You have length, width, and height, right? And then time. And you all sit here, and I move around in length, width, and height. And so the question is there, so that's 4 dimensions, right? 3 in space, 1 in time. Is there a 5th dimension? Is there something beyond length, width, and height? And so in this particular theory in physics, it's postulated that there is a 5th dimension. That 5th dimension is not time. It is an extra dimension of physical space. All right. Here we go again, right? And I was very fascinated by this idea. I have a little interest in things that may sound off the beaten path. But I was interested in it only if there is a way to test that theory scientifically. So let's get a little feel for what this brain world theory is about. Here is our world with all our galaxies and all those shadows I told you about. Us, we are right on this. It claims that there's another direction. Must be inaccessible to us. Another direction, physical direction to reality. And in this direction, you may have another universe. They call it's B-R-A-N-E, brain world, as in membrane. So you could have another universe parallel to us, and maybe infinitely many of them existing right now. Well, cute idea. Theorists always have these things. But how on earth can you test if there's another direction if we can't get out of our world? It sounds weird to say to leave length, width, and height, right? Well, this is the set of hypotheses under this theory, and it naturally extends Einstein's theory. It generalizes all the equations, all that stuff with the bending of light, to this context. And so a colleague of mine, Chuck Keaton, an astronomer, he's at Rutgers University, we collaborated on how on earth would you test this theory. Now, one approach is to use particle accelerators, but there's no way you can possibly test that with the limited human capabilities we have today. All right? And so is this a kind of theory that will just sit there in the world of self-indulgent theorists? We said, if this thing is correct, and we use its equations for how light will behave in that world, it has to produce a shadow pattern. And a shadow pattern with effects in our world. And if it does, is that detectable? But there's one big difference, and I'll share that with you right now. So you have regular black holes in our world. Well, if there is this 5-dimensional universe, that too should have black holes, and I'll tell you why. Early in the universe, with the Big Bang, a lot of microscopic black holes were created. A lot. And in the regular Einstein theory, you'll see it. And in this 5-dimensional theory, you're going to see it in the equations as well. Well, if those things, when I say microscopic, I mean like the size of a nucleus, okay? Literally. The shadow patterns I showed you before were for things of the scale of stars. But now we're going down to the atomic level. Now, in Einstein's theory, which assumes a 4-dimensional world, these microscopic black holes with mass less than that of an asteroid, so I put a little picture of an asteroid to remind you, there is something called Hawking evaporation. And what that is really saying is that by today those things would have all fizzled out. Good. The universe is expanding. It started from this very hot, inhomogeneous, dense beginning. And so this is why you don't worry about that. But if you do the same analysis in brain world theory, you'd become surprised. The black holes end up being cooler than the ones in Einstein's theory. And so what it predicts, it has a different temperature law, is that those black holes with a mass less than that of an asteroid would still survive to today. And that was our hook in. That should be testable. So if these 5-dimensional black holes are existing today, though the size of, say, a nucleus, but massive, the mass of an actual asteroid, we could predict its signature. So this is a chain of reasoning Chuck Keaton and I went through. And let's continue the chain of reasoning. So how do you detect one of them? We had to develop a theory of gravitational lensing for objects that are about the size of a nucleus and the mass of an asteroid. So how on earth would you figure out the shadow pattern for that? Well, it turns out that you're dealing with scales so small that you have to use wave optics. And everyone has seen wave optics. You have a still pond, and you drop a pebble, and you get ripples. And so what we're saying is if a brain world black hole exists, it will act on light. The light is like the pond, and create intrinsic ripples throughout it. These ripples are going to create a special kind of shadow pattern. And here I try to give you a sense of what it would look like. And this is an interference fringe pattern. For those of you doing physics in high school, I'm sure you have seen this. And so what we predicted is that if you have a source of light, that's the pond, there's certain sources of light called gamma ray bursts. They suddenly burst out a lot of radiation. It comes out uniformly across. And if a brain world black hole passes in front of that, that's like the pebble falling in the pond. And the energy profile would follow this curve. If there's no brain world black hole, the energy profile of the gamma ray burst will just be a straight dashed line like that. Good. Well, then we also showed that the energy scale at which this can happen is accessible to a satellite launched by NASA a few years ago. It's a satellite that's designed to look at gamma ray bursts. And in fact, one of his undergraduates, Christina Kramick, has been involved in searching the data of these gamma ray burst energy spectra to see if you could find a wiggle. So it's a kind of thing that I think is great for undergraduates and graduate students. But here's an example of where this satellite out there right now is collecting data, looking across the sky for these sudden bursts of gamma ray radiation. And we're going to analyze it to see if that wiggle exists. So that concludes the story, but it tells you we should have a lot of respect for shadows. It have a lot of hidden secrets. Thank you.